Okay. Now let's have a closer look at the definition of differentiability. Differentiability means that this limit h goes to 0, fa plus h minus fa minus ah is 0. Okay, so a quantity goes to 0 if and only if the norm goes to 0. Therefore, we can also replace our definition by taking the norm around the numerator of this definition. Okay, this is the first remark. The second remark, let eta h to be fa plus h minus fa minus ah. Then eta is defined also in the R-neighborhood of A and map into Rm. Okay, because the right hand side of the definition of eta are pointers in Rm. Therefore, eta is mapped into Rm. And also, we have this property, limit h goes to 0, eta h divided by the norm of h is 0. And fa plus h minus fa is ah plus eta h. Okay, so this is a direct consequence of the differentiability. So the eta here is determined by the matrix A and our map F. So it is not free. And from this limit 0, since this limit is 0, we say that the numerator is so-called higher order term. So the differentiability is usually defined in this way: fa plus h minus fa equal ah plus higher order term with respect to the norm of h. So this is our eta h. But because this notation seems not very explicit, therefore we will try to avoid using this notation. Avoid using. We will avoid using this notation. But I will just tell you, many people use this notation. Use this equality to be the definition of the differentiability. Okay. Now we go to the matrix A. So we have mentioned that the matrix A is unique. So if A is not unique, you could not denote A to be the derivative of A. If there are several matrices A satisfying our definition, so it is not certain which one is the derivative. Fortunately, the matrix A is unique, therefore this is not a problem. Now we'll prove this result, and we also want to know what the matrix A is. We want to determine this matrix A. How to do this? Now we determine the matrix A, that is the derivative of f at the point A. For this purpose, we write, because f is a map from a neighborhood of A to Rm, so f has m component, so we can write f to be f1 fm. Okay, and also we can write A to be the matrix A. The A has m rows. So the AI is the ith row of A. Okay, so using this notation, let us consider the definition of the differentiability, that is this equality, where eta satisfies this limit 0 condition. Okay, let's have a look on this equality. We take the ith component. This equality is an equality in Rm. Both sides of this equality are elements of Rm. Okay, therefore we can consider the ith component of this equality. The ith component of this equality, I have no space, I need to go to next page. Our equality is fa plus h minus fa is ah plus eta h. The ith component is fia plus h minus fia equals, this is aih plus eta I h. Why the ith component of ah is aih? We use a useful fact. Why this is true? This is linear algebra. Okay. Maybe you forgot this. I will tell you. So ah is a1 am h. By the metric computation, the laws of computation, this is a1h amh. Therefore, the ith component of ah is aih. So we have this equality. Okay, we have this equality. Now, what this means? Remember that our eta satisfies this condition. And also we know that eta I is the ith component of eta. Therefore, eta ih is a real number. Eta I is a real valued function. This is the absolute value will not greater than the norm of eta h. So we conclude that h goes to 0, eta I h divided by the norm of h is also 0. So from this limit 0 and this equality, and remember our definition of differentiability of real valued function. Now our fi is real valued. So this means that fi is differentiable. The ith component of fi is differentiable. And this ai is nothing but the gradient of fi at the point A. Okay? So our A is a1 am. Therefore, it is the gradient of f1, the gradient of fm. So this is the matrix d1 f1, dn f1, d1 fm, dn fm. So we determined the matrix in our definition. So this also tells us that the matrix A is unique. Okay, so this is this justified to define the A as the derivative of f at the point A. And also the A is nothing but the Jacobian matrix. We introduced previously the Jacobian matrix of f at the point A. Okay, so when we introduce the Jacobian matrix, we denote this by f prime A. So the notation is consistent with our definition because we call this a f prime A. This is the reason why we call the Jacobian, why we denote the Jacobian matrix by f prime a. Okay. So we have determined the matrix A. Next, we will study the consequence of the differentiability. Well, we study the consequence of differentiability. The first thing is the relation between differentiability and the continuity. We will prove that if f is differentiable at a point, then it will also be continuous at a point. So proposition. If f is differentiable at the point A, then f is continuous at A. The proof is easy. Proof. Differentiable means that limit h goes to 0, fa plus h minus fa minus ah, or maybe we use another argument. F is differentiable at A, so there exists an eta defined such that fa plus h minus fa is ah. Ah is f prime h plus eta h. Okay, therefore taking their norm, fa plus h minus fa will not greater than the norm of f prime h plus the norm of eta h. But f prime a is an n by n matrix, so the terms in the first pair of bar, the norm on the right hand side is a matrix multiplied by a column vector ah. By the property of matrix norm, ah less than matrix norm and the norm of h. By this property, we see that the right hand side will not greater than the norm of f prime h a, and the norm of h plus the norm of eta h. Since eta satisfies this condition, eta h, we know that as h goes to 0, eta h must goes to 0. Okay, this means that eta h goes to 0. So this term goes to 0 as h goes to 0, and the first term also goes to 0 because the norm of the matrix f prime a is unchanged. But here we have in factor the norm of h. So the right hand side goes to 0 as h goes to 0. So this proves that the limit x goes to a fx minus fa, this is nothing but the limit of h goes to 0, fa plus h minus fa. This is 0 by the previous estimate, the inequality, and the right hand side goes to 0, so the limit is 0. So this means that f is continuous at a. So the proposition is proved.